think we can start this 3 o'clock. So, good afternoon. As we said 2 days ago, today we want to analyze this case study, which is quite an interesting case study. This building that was built out of Ixlam in London some years ago, some 10 years ago, as you can see, 2008. As I was mentioning last time, this building originally was supposed to be made of reinforced concrete. It was, you can see, it's a 9-story building. Some information about the project. The start of the project was in June 2007. April 2008 started with assembly on site, assembly of people on site. And May 2008, basically after 1 month, the CLT building was completed. So 1 month time to build this 9-story made of CLT. Some key facts for the developer. So, basically, using timber for this kind of construction had a drawback, an inconvenience. So, what this inconvenience was the cost, the actual cost of the material. So, the material itself, timber, which had to be imported from Austria, cost basically 30% more compared to reinforced concrete. So, if one has to make a decision only based on the cost of the material, of course, this would be a loser. CLT would be the loser, definitely. However, if you want to look at the whole program of construction, as you can see here, using CLT meant that basically the building would have been ready in 17 weeks in advance. So we would have a saving in time of about 17 weeks using CLT. So 17 weeks less for a whole project. Now, estimating the saving of money due to the reduced cost and comparing this estimation with actually the higher cost of the material itself made anyway CLT as a convenient solution. In other words, the saving time basically was by far greater than this increasing cost due to the fact the material itself was more expensive. So in the end, as I said last day, the decision was made to use CLT basically because the program was shorter. So this allowed the developer to have the building built and ready 17 weeks in advance. Of course, it depends on when you build your building. Probably if you build in L'Aquila, or I would say in any Italian city different from Milan or Rome, I guess, probably this saving time is not so important. But if you build in a very big and crowded, busy city like London, Milan, or Rome, actually you can estimate this advantage in time is a very important parameter. So this will make the whole project more convenient. So just the fact for your information is that the speed the highest speed of construction, this kind of building, in some cases may make the building actually more convenient, even though the material may cost more, like in this case. I would say this in general. Also in Italy, probably if you compare the cost of reinforced concrete to timber, anyway with timber you're going to spend a little bit more, so it's more expensive. However, just keep in mind that the saving time may make the timber project preferable compared to a reinforced concrete project. Some general information: it was the highest solid timber building worldwide, just under 30 meters. Later on, I'm going to show you another higher building that has been completed just a few years ago. 8 stories. 8 stories made of cross-slab panels, which are constructed above a podium slab. So there is a first ground floor made of reinforced concrete. This is a residential building, so 29 living units. And the whole building is made of CLT, including the lift and the lift shaft and the staircase. In terms of sustainability, you can get a very excellent eco rating, 760 tons of bound CO2. Why? Because basically when you do the sustainability assessment of a building like this, as you know, you want to check how many tons of CO2 you have subtracted from the atmosphere, or how many you have spent in order to make the building. Now, in this case, the material itself, the timber, is actually having, it has some embodied CO2 inside. So in other words, of course you're going to spend some CO2, you're going to consume some CO2 to make the building, but the wood itself contains CO2. So if you do the balance, you'll find out that in the end you have you have basically embodied more CO2 than what you have spent to build the building. Because it's simply because it's made of wood. Wood itself has some CO2 inside. So in other words, if you do your sustainability assessment, you can get a very good rating of excellent if you build a building like this. Some number now, 905 cubic meter of CLT panels, or if you want 7,000 square meter of panels. Of course, this is all made of certified wood, so the wood used to build these panels comes from forests that are sustainably managed. So it's not wood coming illegally from outside Europe or cut illegally from somewhere. The walls are usually made from 5 layers, so 128 millimeter thick panels. The floors are again 5 layers, 146 millimeter thick. Now, the very interesting information is this. As you can see here, the erection time approximately 3 days per story. So to build one story here, it basically took 3 days of a group of 4 carpenters. Of course, they were very experienced carpenters, not like me or you. It was 4 people that was very well trained. But anyway, one floor in 3 days is something which is quite amazing. If you think about one floor like this made of reinforced concrete, you have as a minimum to do 2 placements of concrete. One for the vertical structure, one for the floors. It means you have to wait minimum, I would say, 10 days for one, 10 days for the other. Minimum, so 20 days rather than 3 days. Completely different approach. In fact, just keep in mind that one of the advantages of those buildings is the speed of construction, because they are highly prefabricated. And you can see the erection team for carpenters. This is the map. Actually, the plans of the building, as you can see, there are all panels. There are double panels for the reason of fire safety around the staircase and around the lift shaft. Now, in terms of strength, of course, London is not an earthquake-prone area like here. In this case, usually the gravity load governs the design. And the weakest link in this case was due to the fact that the type of construction is, in this case, like in most of the cases when we talk about crossland, is a platform construction. So do you remember the meaning of platform construction we discussed last Monday? What does it mean, platform construction? It means that you place first the walls, then on top of the walls the floors, and then on top of the floors, not on top of the floors, are the walls. Of course, the walls must be aligned, but there is in between the 2 walls there is the floor panel, which is squashed between the 2 walls. Okay, this is platform construction. Of course, it's not the best solution. Actually, it's probably the worst solution. Because the best solution would be to have the 2 walls one above the other and the floor outside. But in terms of construction, much easier, I would say easier to build in this way. Platform construction than with a balloon construction. Much easier, so that's why it is used, the platform construction. So the weakest link comes from the fact that we have a floor which has a resistance 2.70 Newton per square millimeter perpendicular to the grain, and it is squashed by walls which have 22 Newton per square millimeter resistance by 20. So at the end, this is almost less than 1/10 from this, and this is going to govern the design. So that's why they have, particularly to the lower story, when the load becomes higher and higher, they have to strengthen, you see here, the connection between the wall and the floor. And the way to strengthen was, as we already discussed several times before, was to use some reinforcement, some screws, self-tapping screws that in some way help transfer this pressure from the side, from the edge of from the wall itself, till inside the panel itself. So in other words, with the screws we're going to distribute this load, concentrated load above and beneath the wall into a larger area within the floor itself. Okay? So that's the kind of reinforcement that was done here. So here you can see the type of connection. In this case, we have no different connectors for resisting the uplifting force and for resisting the shear force. So we have only one type of connection, this kind of angle brackets connected with screws and nails, that functions as a hold downs when they are placed at the end of the wall, and as an angle brackets when they are placed in the middle of the wall. So no difference between hold down and angle brackets, only use of all angle brackets. Why is that? Because, again, we are talking about design and construction building in London, which is not a seismic active region. It's also not very strong wind region, meaning that the horizontal forces don't play such an important role like here, for example. The hold down, they're mostly meant to resist to uplifting, so axial force, but here in this kind of building, we don't have the very high uplifting forces because we don't have earthquake, and the wind is not very strong. Okay? And then you have the same point of the building, which is quite important because we're talking about 9-story building. A very important problem talking about any multi-story building with residential destination is about acoustics. So, as you know, acoustic is a serious problem, even with reinforced concrete. Even with reinforced concrete, sometimes we have a problem that if you have two different packages, one above, one below, very often who lives below can hear what they do above and vice versa. So how can we solve the problem of acoustic? Just keep in mind that acoustic separation depends on the density of the material in the home. So if you're a concrete, you have 2,500 kilograms per square meter. If you're wood, you have only 500, so 5 times less. Meaning that also the separation, the acoustic separation, 5 times less. So with timber, we might have a problem. So how to solve this problem? We have different details. You can see here some possible details for party walls and floors. And for example, you see that we have a double wall at the interface between staircases and living units, because in this way, first we have a larger fire resistance, but also we have a larger acoustic resistance. You see two panels with acoustic insulation in between. Of course, the simple solution is this one, where the acoustic separation is very poor, and then you have different possibilities in order to do the acoustic separation. The simple way is, as you can see here, to use like here a 60 mm cement screen on top of the panel, then a footstep sound insulation board, and then 70 mm bottoming protection around basically another layer having 1,800 kilograms per cubic meter of density, so another heavy layer. So as you can see, in order to, in some way, have less acoustic problem above the timber structure, we have to put a number of layers more or less heavy, like gravel, like sand, like cement, and so on, in order to increase the mass. Other possibilities with, for example, some resilient sealing below. And you see also, you can go to solution much more performing, like having two double floor, and so on. So 5 In terms of fire, there was a minimum fire resistance required in this building, because we're talking about national building. So, as you can see here, this dashed lines shows some walls that had to be at least 30 minutes fire resistance. Now, we haven't spoken so far about fire resistance. I will give you a final lecture discussing a little bit about fire resistance, because of course for timber it's important, being combustible material. So 30 minutes of fire resistance basically means that if you have on either side of this wall a fire, this wall should be able to stay in place to basically to resist the vertical load for 30 minutes at least, and during these 30 minutes it shouldn't allow some flames to go through, and during these 30 minutes it should not transfer too much heat from one side to the other. So what we usually say REI in Italian, which is resistance, isolation, and isolation from the thermal, from the heat, and isolation also from the smell. There are three basically parameters. We will say later on. So basically, all these walls within the dashed line had to be at least 30 minutes fire resistance, which are basically the walls between the internal corridors, living space, or between, let's say, the daily or the night rooms and the corridor. Then 60 minutes separation between different units, and between the units and the egress system. And 120 minutes, you see all these walls around the lift shaft and the staircase. Now, how can we achieve these numbers using timber? We will see later on that using cross slab is not very hard to achieve those numbers, because timber is an insulating material. Of course, it's a combustible material, so we can have that our wall starts, for example, our wall or our floor start burning, but the time that is needed for this cross-section to reduce to zero is very high. And most of all, when the external layer is burning, if you measure the temperature just 60 millimeters inside, you will find still the ambient temperature, because the material is insulated. While instead, if you use steel, it takes just a few minutes for the heat to move from the surface inside, because the steel, of course, it's a very good conductor, unlike timber. So in this case, they did some tests, and they found out that there is this charging rate of 0.67 millimeter of minutes, meaning that a panel like this, for a panel like this, it takes 1 minute to lose point less than 1 millimeter. So if you expose this panel to the fire, it will take more or less 0.67 millimeter. It will take 1 minute in order to lose 0.67 millimeter of wood after combustion. In this way, it's very simple to do a calculation. You can calculate, for example, if you have if, for example, this panel must have a fire resistance of 60 minutes, 60 minutes times 0.67 means more or less 30 millimeters. Means that after 60 minutes, you will get only 30 millimeters or only one layer of the panel would be low. There would still be another 4 layers to keep the load. Okay? So in the end, the results of this experimental campaign was that the fire resistance of all load-bearing components was 90 minutes. So one panel like this can resist up to 90 minutes. The fire resistance between apartment lift shaft and staircase was 120 minutes because 2 panels were used. So if you look at here around the lift shaft, where 120 minutes fire resistance was required, here a double panel was used in order to get a higher fire resistance. Some photos about yes, interesting thing. they didn't have to use any sprinkler system. You know what is a sprinkler system? It's kind of system with using water that can spray some water once the fire is detected. For example, here we have fire sprinkler inside here. Probably not see anything. There is something that no, this is just we don't have. But why we don't have? Because we don't have also lots of combustible materials inside. Here the combustible material is basically this in our cell. Nothing else can make, of course, the clothes at the end of the surface. For this reason, probably we don't have such an important risk to impose the use of sprinkler and fire detectors. Here we don't have either sprinkler or fire detector. We just have the board indicating that we have to go away. Okay, so in this case again, although the building was quite high, there was quite a lot of thousands of cubic meter wood, which is potentially combustible. Non-sprinkler system was required. Okay, some photos about the construction. You can see here this group of 4 skillful carpenters. So here, we are on the top of one of the floor. So this is the floor, basically. So first you see they place these angle brackets all around, already screwed. And then you see the panel is coming, and then the angle brackets are connected to the panel, the wall panel. Of course, the panels are as long as the whole wall, if possible. They are already cut. So all these panels you can see here with the cut were produced in Austria, and they were shipped by lorries from Austria to London. Temporary prop here, as we said, we have a box without the lid, meaning that the structure is not very stable, and as I said, we need to use some temporary props like here. Another photo. This is the building upon completion towards the end of the project. Okay, another example. This is an Italian example, the 4-story CLT building. Here you can see a sequence of some photos showing the process of construction. So first, you see, we start by digging the natural soil till the required level, 1.2 meters. Then we call in Italian tessuto, non tessuto, I don't know exactly how to say in English, basically a kind of membrane that may in some way protect from the water. It's not actually, it allows for the vapor to go through. Usually we use this membrane here, basically underneath the foundation. Then we do the first layer, which is not a real structural concrete. Italian we call marrone. It's a kind of first layer of very poor concrete, if you want, just to make it smooth. Then we have a bituminous waterproof coating all above. Then we have the foundation with all the reinforcement. Concrete foundation slab 30 centimeters. Then we have the small walls above the slab 40 by 65 centimeters. The first levels, the floor is usually made using this igloo, as we call this igloo, to create a ventilation space between the floor. Then another placement of concrete, and then now we are ready to place the walls, the timber walls. Before the timber walls, it's always better to put another bituminous waterproof coating. Then the walls arrive with the slurry, the panels actually. They are discharged from the lorry. They are placed, you see, with some temporary bracing. We are talking about here that there are very, if you want, slender walls, so 5 layers, 13 centimeters thick. First story, then the floor, 5 layers. If you look above the wall, as you can see, there is this black strip. This black strip is a sound separating. It's basically a kind of membrane made of rubber that is used to get some kind of noise sound separating layer. The floor is used as a platform for the second story. Here you can see the all downs and the angle brackets. You can also see this kind of strips, black and white. So those strips, black and whites, are kind of tape that is used to cover the joints between vertical panel and horizontal panel, in order to make a building which is also air proof. In other words, without this strip here, in the days of very strong wind, you could have some windows around the side. So we need, because of the joints between the panels, so we need to cover the joints using this airproofing stripes. Other photo with again other all down, other brackets and airproofing stripes. This is from outside. This is the roof CFT panel. So as you can see, very slender. You can see with your eye that this panel is actually bending quite a lot, because it's only 6.5 centimeters, so very slender, made of 3 layers. And the structure, you can see a photo of the structure completed and the building completed from outside. Okay. Now, another kind of structural system that can be used in timber structure is what we call cantilever wall panels. In this case, the idea is to use as a lateral load resisting system some cantilever, vertical cantilever made of solid panels. Could be made of glulam, could be made of crosslam, could be made of LVL. Instead, for the resistance to the gravity load, in this case, post and beam timber structure is used. So post and beam means columns and beams being connected. So this means in this case, as you can see here, we have different members for the resistance to the lateral load. So the lateral load is taken by these cantilever walls, and the gravity load is resisted by this system of posts. Post in English means colonna, in Italiano column, and beams, which are usually beam connected. So in the end, we have a structure where we have a number of cantilevers which are connected with the structure being connected to resist to the vertical load. So if you want, we have structure for vertical load. You will have the uniform distributed load actually here. While instead, this one, which is the cantilever, is taking all the horizontal forces. Okay? So the cantilever is the lateral load resisting system, while instead the post and beams are the gravity load resisting system. So here the wall can be made, you see, by assembling together some simple rectangular elements. Those rectangular elements can be solid, or also can be, like in this case, made by a frame made of glulam, and with a sheathing, top and bottom sheathing made of MDF. The connection of this panel to the foundation can be obtained using, for example, this steel hub that is then connected with the wall to the foundation using epoxy rods. So using rods which are glued inside the wood. On one side, and glued to the foundation, or actually, more than glue, connected to the foundation using some mortar on the opposite side. This is a kind of photo of this detail, and this is what would be the result of an experimental testing when we have here the wall, we were going to push the wall laterally, like in the case of an earthquake. So if you push the wall tends to uplift here, and of course we may have a failure in the groove between connecting the rocks with the wood panel itself. So this system, you can see here, is particularly suitable for open space, because in this case, having a system made of posts and beams, you can have also some spans of from 5 to 8 meter grade long. Of course, with this kind of building, we cannot go too much in elevation, 4 to 5 story, and the behavior factor is a kind of low value, could be, I would say, 1.5, like in the case of the building you're designing your project. This is a rendering of this kind of structure, so those walls here are the lateral resisting system. Then you have the floors, and the beams, and then the columns inside. This is another kind of connection between this cantilever wall made of glulam and the foundation itself, using a steel plate with some bolts. A kind of advanced connection is this one, where an innovative viscous damper has been used. So here this is a kind of viscous damper connected to the wood using this kind of pre-drill screws. So anytime that the wall moves due to the horizontal force, it tends to rotate. So we have some energy dissipation inside this device due to the fact that the wall is going to rock, so to move, and then the device is going to be stretched. So it then goes up and down. Inside this device there is a lead, piombo, which in some way, by deforming itself, is going to dissipate a significant amount of energy. So that's why this element is called energy dissipator, because it's going to dissipate energy during the typical rocking motion used by an earthquake. Here is a photo of this damper. Another possibility is to pre-stress the walls, for example these LDL walls, directly to the foundation using some bars or pre-stressing strength inside this cavity. So the idea is that we could think about, for example, using a cross-lamp panel where one of two planks has been left in order to create this hole, this cavity. Inside this cavity there is a room to include a duct where there is a strength that can be used to pre-stress the wall to the foundation. Between the walls can then be some energy dissipator can then be used in such a way that when an earthquake occurs, so you have one wall, another wall, so here there is this energy dissipation in between. So the walls are basically pre-stressed to the foundation using some tendon. So there is one axial force which keeps the wall tight to the foundation. When an earthquake occurs, if these forces are significant, we can have that this wall starts rocking. So we have in this way, 1, 2. And this dissipator, as you can see, is going to deform. This dissipator is basically could be a piece of steel done this way. So when this is going to deform this way, the dissipator is going to deform. So the wall is going to rock rigidly, the dissipator is going to deform, and then we will have some energy dissipation during an earthquake. The advantage of this system is that at the end of the earthquake, since there is this pre-stressing tendon, always keeping or try to move to step back the wall in the initial position, at the end of the earthquake, we will have this pre-stressing force applied through the dissipator will basically bring back the wall to the original vertical position. So in the end, we don't have this problem of residual deformation typical of the earthquake. You know, after an earthquake, very often buildings they don't fall down. They stand completely some way twisted, so they don't stand straight anymore. They're inclined, but by using this pre-stressing steel here, at the end of the earthquake, the pre-stressing strength can, in some way, create a force that can make the system going back to the position, the straight vertical position where it was before the earthquake. If you can see here the application of this concept to this big building being built in New Zealand. So wall made of MDF, pre-stressed wall, and then in between there are some energy dissipators. Those are the energy dissipators. You can see so some U-shaped metal plates which are connected to other plates which are in turn connected to the wall itself. So when this wall is going to deform, we have that this dissipator is going to deform in this way. So it's going to dissipate energy. This is the lower part where we can connect the strength coming from the top that will apply the constraining force. And this is the timber composite floor that was used at the intermediate story. You can also use moment-resisting frames made of timber. Just a reminder that in terms of timber, we never have a real fully rigid joint, as we said before. We can have a fully rigid joint only if we use glue. Otherwise, we have a semi-rigid connection. So moment-resisting frames, in general, they are suitable for buildings with open spaces, because of course, moment-resisting frames are not very, they don't take a lot of room. Maximum 3 to 4 stories, so with a moment-resisting frame, we can't really build a building higher than 3 to 4 stories. The Q factor, so the Q factor may range from 2.5 to 4, depending on the ductility of the big column joint. If the joint is very ductile, like the one that we will show shortly, then you can get up to 4. So this is a first type of beam column connection using nails and plywood cassets, steel cassets. In this case, we have some loops of nails on the beam, some other on the column, and some other on the opposite beam. Or we may use epoxy glued rods inside the wood, inside the beam, connecting the beam with the column and with the other beam. Another possibility is to use this kind of steel hub connected with the wood using epoxy glued rods, or this would be probably the best possibility to get rid of this portion of the column, which is in some way is subjected to horizontal loads coming from the beam, which are applied perpendicular to the grain, so which are not very in a direction where the resistance of the material is very low. So we can think about removing this piece of wood and replacing it with this metal hub, which can be connected with the wood using these rods here, glued in the timber. There is a version, there is a kind of beam column joints with high ductility with using expanded tube fastener that was developed at the University of Delft in the Netherlands. This joint uses expanded tube fasteners and densified veneer wood. So, for example, for a building like this, we may use in one direction as a bracing system the cantilever walls, and instead you see in the other direction to use the moment-resisting frames. For the moment-resisting frame, the column could be made by a rectangular cross-section, and the beams could be made by two parallel elements. The connection between the two parallel elements and the column could be made using expanded tube fastener arranged along a circle like in the figure. In this case, you see that in addition, on each side of the connecting member, we have the use of what we call densified veneer wood. So densified veneer wood is a wood which has been artificially densified using a press. So the wood itself has been pressed in order to be compressed in order to increase the density and so get a material which is much stronger. So the expanded tube fastener are those metal tubes that you can see here. So the fastener is basically a metal tube. This is one beam, this is the column, this is another beam, and you can see that at the contact between the beam and the column there are densified veneer wood. So this black brown layer is actually two layers. One layer is one plate of densified veneer wood, so we are here. So one layer is the one densified one. So half of this layer is this densified veneer wood glued on one side of the column, and the other half is the other plate glued on the beam. Once we apply to this joint a moment, you can see that we can get a very high deformation within the within the expanded tube fastener. Particularly, the use of this densified veneer wood is in order to make sure that we will have a plastic hinge formation here and not somewhere else. So in other words, having this expanded tube fastener in contact with this very high density linear wood means that we may have the formation of a plastic hinge actually here at the interface. So we can have a very plastic behavior of the fastener itself. This is an example of a real structure being constructed in the Netherlands. The other possibility is to use some pre-stressing cables, pre-stressing tendons, to connect columns, like in this structure, here, some columns with the beams. So this is an example of a pre-stressed timber moment resisting frame, where we have some tendons running into the cavity of the beam. So basically, in this case, so this is a beam, it's a cross-section of a beam that is being made by LVL. So the LVL beam is made by gluing together 4 pieces, done in this way. They are glued together. And then in between there is this cavity where there is a pre-stressing tendon. This tendon, as you can see, is fixed on one side of the column. It runs through all the way through the two beams and the intermediate column, then it ends up on the opposite column. So we have a situation like this. Column, beam, column, beam, column, and the pre-stressing tendon runs in this way. So when pre-stressing this way, the timber column with the timber beam, we may have again, first of all, we may have that these joints become a kind of semi-rigid joint because the columns and the beam are pre-stressed together. So meaning that this joint is going to resist some bending. And then again, like before, we may have that, for example, if we use here outside, if you put some dissipators, during an earthquake, you may have a situation like this. And when the earthquake ends, again, this pre-stressing force makes the system snap back in the vertical position where it was before. So in other words, this pre-stressing tendon is used to keep together the joints, so to ensure that the joints can resist a bending moment, and also to allow the structure to go back to the initial position at the end of the network. So to basically avoid permanent or residual deformation, residual damage at the end of the earthquake. Very often this system here is coupled with some energy dissipators placed here outside at the interface between the two members. Of course, this kind of system that I showed you now is an innovative system, still hard to use, but it has been tested in New Zealand, and in some cases, for a few buildings have been used. One important problem of this system here is due to the fact that in the long term, we can expect some losses in pre-stressing within the tendon. So we will have some losses of pre-stressing force due to creep, shrinkage, all these problems within the timber. Okay. Another kind of system extensively used for multi-story building is what we define as a hybrid system. What do we mean for a hybrid system? We mean, for example, that wood can be mainly used for gravity load resisting systems, whilst other material, for example steel or reinforced concrete, could be used for lateral load resisting systems. So we use different materials and we make two different structures, one for resisting to the gravity load, and the other one for resisting to the lateral load. This is suitable for open spaces, like an office building. We can get up to 10, 15 stories. And of course, the value of the Q factor will depend mostly on the bracing steel that you want. So if you use steel, we will have one value. If you use reinforced concrete walls, for example, we will have another value. So this is an example. Here you see basically a concrete staircase inside, and a system made of posts and beams made of glulam. So again, we have a system where there is a general inner core resisting to bending moment, taking all the lateral forces, and then a system made of timber, posts and beams, resisting the vertical loads. This is another system where instead, in this case, some moment-resisting frames made of steel can be used along the facades, and instead, inside, timber, posts and beams that we use to release the vertical loads. Two significant examples of the hybrid buildings being built in our country. So two 6-story buildings, one constructed in Trieste and one constructed in Cavoli, in province of Venice. They were both built by the same company, original house of Holzbau, and so they both have similar kind of technique. So, the idea is that gravity loads has been resisted by glulam posts and beams. So again, a system like post and beam which are pin connected. So this is the column, these are the beams, this is the connection between plates and fasteners. The beam, as you can see, is made, it has an inverted T shape, so the beam is made this way. Weight of what actually, not the weight. So this is the beam made of glulam. And here we have floor panels made again of glulam. Glulam which are placed on the edge. So columns, beams made of glulam, and glulam beams used on the edge as floor panels to connect it with screws. So basically the panels are made by glulam beams which are produced with a depth of 2 meters, and then those beams basically were placed were used on the edge as floor panels and connected using basically screw connections. Some photos. So here you can see the glulam column, the glulam beams, and the glulam floor panels on top. And here you can see the connection between the glulam panels and the beams using inclined screws. Just a reminder that inclined screws, when the screws are being used inclined, because this way you can get the maximum thickness. In this case, as you can see, there is a staircase made of reinforced concrete which is going to resist all the lateral forces. So all the structure you can see here, posts, beams, and floor panels, they are basically resisting only the vertical load. When you said all the lateral load is being taken by this reinforced concrete staircase. So in this case, as you can see, the type of construction, first the staircase is made of reinforced concrete, well, first the foundation, then the staircase is made of reinforced concrete were built, and then the whole timber structure was built with this kind of connection between staircase and beam itself. The facades were made of light frame panels prefabricated offsite and connected to the glulam posts and beams. So we have panels like this, they're all prefabricated. Here you can see the prefabrication of the panel, placement of the panel on the lorry, then delivery to the building site, and train to position. Another photo from outside, looking at the building being under construction. And this is the skin, the one that the kind of typical resistance mechanism. So we have a plate foundation, we have the staircase, resisting like a big cantilever to the lateral forces, and instead the timber structure is made by posts and beams, resisting mostly to the vertical, to the ground below. Erection sequence, first we start with the foundation, then we build the lift shafts and the staircase, and then we start building the timber structures. So, vertical structure, then we have a floor, another floor, and so on, until we get to the top of the structure. Construction time, September 2011, November 2011. So a couple of months to build the whole timber structure. Again, also here, most of the time was spent to build the reinforced concrete staircase, and instead timber structure was built very fast. One problem important that we need always to take into account when we design the residential building is the problem of vibrations. In order to get rid of this problem, the rule is to discontinue floor panels on the supporting glulam beams to avoid vibration transmission. So the idea is that if we have a continuous floor panel, of course if I'm going to jump on one side, also the people being on the opposite side will feel the vibration. So in order to avoid the transmission of this vibration, it's a good rule to split, rather than having a continuous span, to have two separate spans, one on the side, one on the other. Some details about the load supporting timber beams, the floors, the isolation, and so on. insulation. The external insulation is usually made using cork panel. And also here it's important to ensure air tightness using this kind of tape, with which we should just cover the joints between panels. For example, you can see here 20 km containers were used. Acoustic separation, so here we have this rubber strip just underneath the wall panel, but the contact between the wall panel and the timber beam. So 10 km rubber strip were used. Another example is a multi-story building called modular system, where everything again is prefabricated. So in this case, the system is made by wood double columns and a hybrid slab timber concrete composite structure. You can see here an example of construction. So the whole facade panel is delivered to the building site, and it is lifted to position. Those are the prefabricated timber concrete composite panels. So the whole timber concrete composite panel is prefabricated offside. Prefabricated offside and then placed above inside this towers that you can see here at the end. So the vertical panel has already included some columns with this kind of bars protruding from the top of the column. And in this prefabricated floor panel there are some holes. So they are basically lifted into position, and those holes will go inside this big downward here. Another photo of the panels being placed on the building. In order to get the continuity of the concrete slab, we have this kind of holes here that later on will be filled using some mortar, basically iron resistance mortar, to get the continuity of the slab.
There is the glue here, or they are just...
No, they're just this way. Yes. Step this one. This is using some mortar. Temporary props. This is a detail from underneath those vertical towers we saw before. Consider those panels are quite heavy because they're made of timber and concrete. So they basically stay in place from gravity. They cannot be uplifted. Another photo that shows us, for example, the use of building services underneath the reinforced concrete between the timber beams. And this is the 8 stories CRE building top beam of the beam building of scale using this technology. The last example, interesting to see, is what can be regarded as the tallest timber building in the world, which is this 14-story building in Bergen, in Norway. This is a drawing from outside. So this is the building. It's called the tree. A net area of 5,230 square meters. It has 62 apartments. The work started in April 2014, and the residents could start living there in autumn 2015. So, this system here is made with a structure which is quite different from the system we saw before. First of all, as you can see, there is a kind of glue-lamp truss system. So the main structural system is this glue-lamp truss system, which makes this building as a huge cantilever fixed on the floor and free to move on the top. Inside this building, some modular units have been used. So the building is an assembly of a number of those timber frame modules you can see here. compliant with the passing out standard, meaning that they are done very well with our very high isolation, thermal isolation, in order to get a very good thermal performance. So this is the structural skeleton of the building. It is like a cabinet rack for modules, so like the cabinet rack that you use in the office to file some documents. So there is a glulam load carrying frame, which is this frame you can see here, 45-meter high. We have 550 cubic meter of glulam and 385 cubic meter of CLT. This structure rests on the top of a reinforced concrete foundation garage, which is supported by some pipe foundations. It is a lightweight building, and if you can see here, this is the typical plan. To cover this plan, 6 units were used. You can see here that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So the floor is made by 3 fabricated units. So 1 unit is basically what I showed before, so this would be 1 unit. But this unit has inside everything. There's already the services, the plants, the toilet, everything is already ready inside. Sometimes also the furniture using IKEA, of course we are very familiar with Sweden. So the whole module arrived already ready to be used on the building site. And this module is then placed inside here and connected to each other and connected also to the main structural element. Just note that the main structural system is basically this structure you can see here. So there is this 3-dimensional truss system made of very big ruler members, which is a truss with connection. And then you can see that we have 2 very strong plates. Those plates, 1 and 2, those floors, are made of reinforced concrete. So in the end, the building, if you want, is like a cabinet, as we said before, a cabinet like this, where we have this truss system. With this very rigid floors made of reinforced concrete. And then on top of these floors, we place these stacks of units. So the units are basically stacked, those units are stacked one above the other, and they are all supported by these reinforced concrete floors. So in the end, these stacks of units are connected together. They are not connected to the main structure, they are just connected to the main structure through the foundation. So it's like basically having, if you want, a main structure, a foundation, another strong floor here, and this stack 1, 2, 3, 4, 5 above, which in some way acts as an independent building just placed on top of this foundation here. Okay? Then we have another one here, independent, and then we have another one above here. Is it clear? It's a kind of strange system, but if you look, for example, at a very tall building, the very tall towers that are built in the big cities in the world, very often we have this kind of structure. So we have some main floors, very rigid and very stiff, made of reinforced concrete, also to achieve significant fire resistance, because they are made by non-combustible material. And then on top of this, we have these stacks of modules, all connected together, but not connected to the main structure, just founded with this foundation here made of the floor itself. Okay? So, glulam carries on vertical load, the structure you can see here. The concrete decks, so 1 and 2, serve as extra weight. roof and platform for modules. They are using as a kind of foundation for the modules, which are one stack above the other. Prefabricated timber frame building modules are inserted into the cabinet rack, so they are just inserted inside. CLT is used in the staircases, elevator shaft, and some inner walls and balconies, so the CLT member is independent. CLT is not structurally connected to the glulam. So here, as you can see, the main structural system is made of glulam. A three-dimensional frame, spatial frame. The prefabricated modules are stacked up to 4 levels, connected to the main structure at the base. The glulam section are those sections you can see here. So the glulam section is basically 495 by 495, so it's quite big. So the beam is half meter by half meter. We can't really prefabricate a building so large. So what they do, usually they prefabricate, they start constructing 3 rectangular cross section, 165 by 495, and then they are block glued. So after they are glued together along this larger surface in order to get the unique, the solid cross section. So here you can see a typical joint using dowels and steel plates. These are quite massive. Another photo is loaded in steel plates and dowels. And here you can see the connection between the first vertical member and the foundations. So rebars welded to bed plate here, casted into pillar with grouting mortar. Then you will have some metal plates and some dowels which are placed to connect the timber across the steel. Erection sequence. So starting from the parking, the basement, so reinforced concrete from the foundation, the first wall and the first floor. Then you see we have a stack of 4 level modules which are independent. Then we started with the construction of the structural system of the big building with the glulam and the crosslam. One more module. Then here we have basically this blue structure is independent. The brown one is also independent. Then this first reinforced concrete frog is casted in order to create the base for a new stack of 4 modules, 5 modules. Another vertical structure made of glulam, another floor made of reinforced concrete, until another 3 or 4 until the end, until the top. And then the facade are used in order to basically clad the whole building. Some rendering from outside and inside the building itself. Okay, last thing I wanted to discuss with you before we move to the next presentation, which is about seismic design, is the use of passive base isolation. So passive base isolation will be the subject, one of the most important subjects of the course Earthquake Engineering you will follow next year. So here in this course we don't say anything of particular, just I wanted to mention that passive base isolation can be used also for timber buildings. Of course, they can be used for any material. Usually they are used for reinforced concrete buildings, but they can also be used for timber buildings. And we have some examples here in L'Aquila, as you know. The Progetto Case has half of the buildings more or less made of reinforced concrete, which are basically supported by plates, base isolated. And the other half of the buildings are made of timber. I would say 25% out of light frame structure, the other 25% out of crossland. They are all passive base isolated. So the idea is to disconnect the building from the foundation, probably all of you know. So the whole building, as you can see, is supported by a big plate made of reinforced concrete. The big plate is disconnected by the foundation, by this pillar, using some isolator. There are different kinds of isolator. So the idea is that very roughly, if you want very simple way, that if an earthquake strikes, then of course everything will move, will vibrate, but the building will stand still. More or less, because as you know, some of you were in one of these buildings in this earthquake 2 years ago, the displacement demand was still significant. So the building didn't actually stand still. The building started moving like rolling, moving very slowly, but moving quite a lot. In fact, you can see from some videos the people who were inside, they all went very fast outside. Because they could feel very well the earthquake. Of course, the important thing, with respect to a building which was without passive base isolation, the displacement perhaps was big, but the acceleration was low. If you remember the video that we saw yesterday, the timber building without passive base isolation, maybe on the top of this building the displacement demand was perhaps lower than this, but the acceleration was much stronger. Now, is it better to have a structure which moves more but slowly, or a structure that moves less but very fast? Exactly, it's better to have a structure that moves even more, even, say, not 1 meter, even if it was 1 meter, but if you move slowly, it's much better if you have maybe 30 centimeters but very fast. With a 30 centimeters very fast, you feel yourself on the ground immediately. Because of course, as we said yesterday, well, if you know that earthquake is coming, you can brace yourself, but you never know when the earthquake is coming. If you get immediately the strong, I would say, load of the earthquake, you are without understanding immediately on the floor. So the idea of this isolator here, of course, is really to decrease the acceleration. So the displacement is still be important, but the acceleration is lower, and so is the damage to the person and to the things that you have inside. This is of course suitable for any type of building. For timber, you have the additional advantage compared to concrete, that's the weight. The weight of this building, made of timber, will be more or less 1/4 of the weight of the building, of the same building made of reinforced concrete. Meaning that you can spend much less money when it comes to build and design this plate, and when it comes also to build and design the isolator. So for timber building is actually better because you spend less money for the isolation. However, for the timber building, you need to be careful about the fact that having a very lightweight building, what could it happen? If, for example, if you had instead an earthquake, you have a wind, could happen that the isolator starts working also for the wind. The idea is that the isolator should work only for the earthquake and not for all the earthquake. The idea is that you should design the isolator in order to make it work when you have the earthquake or the ultimate mistake, not when you have a small earthquake. The problem is that since the building is very lightweight, if there is a strong wind, the isolator may move also for a not very strong wind, and then you start having a building which is moving too much. And who is inside is not very happy to keep on moving. You know, if you move too much, first the people they are scared because they don't know that they're moving, they think about an earthquake, instead it's a wind, then they get some sickness, this kind of thing. So for the timber, we need to be very careful when we design to make sure that there is a kind of stop system or something which prevents the building from moving when there is either a too low intensity earthquake or a wind itself. So we should have a kind of stop system that once you have a strong earthquake, this stop system in some way is broken, and then the system starts working, but not before. Okay?
In questi casi la sollecitazione per innescare l'isolatore è la stessa situazione, cioè è uguale sia per il cemento armato che per il legno, oppure per il legno è differente?
Well, I should ask you, what do you think? Is the same for timber or for...
Secondo me dipende, cioè se dipende dalla connessione tra l'isolatore, il pilastro dell'isolatore e la piastra sopra l'isolatore.
Okay, but when it comes to calculate the stresses acting on the base isolator, this stress depends on what? It depends on the horizontal force. The horizontal force is the same for a reinforced concrete building and for a timber building? Yes or no? No. For the earthquake is different. How much will be more or less the ratio between the two? More or less. No, but then no. But just remember, the set weight of concrete is 2,500 kilograms per cubic meter. The set weight of timber is 600, 500, let's say 500. So more or less a ratio of 5. So, roughly speaking, since this is behaving elastically, more or less you can say, if you place on top of this plate here a timber building, you can expect that the forces acting on the building and then acting on the isolator will be 1/5 of the forces that would act on the same building made of reinforced concrete. Okay? So it's much less. So you can reduce for sure the thickness of this plate, and also the isolator can be smaller because the force is there. On the other hand, I could ask you, what about the wind? Is there any difference in the horizontal force due to the wind if you have a timber building or if you have a reinforced concrete building? What's the difference? The wind forces depends on what? On the surface. Is it different surface if you're timber or reinforced concrete? No. Unless you have a very flexible structure, which is never the case, it starts resonating with the wind, the force is exactly the same. So the force of the wind is exactly the same. So if the force of the wind is going to govern the design, then there is a problem. Then you cannot use the isolator. Okay? So you need to be careful. In fact, this passive base isolation is never used if you have a too tall building. You see, if you have a too tall building, in this case, the demand of horizontal force due to the wind prevails on the demand due to the earthquake. And then you cannot use the isolator anymore, because the isolator is going to move from the wind and not from the earthquake. Okay?
Questo lo fa il progettista ingegnere oppure chi produce l'isolatore?
That's another good question. Who do you think is in charge once this has been built? First of all, you need to do a project design. This design must be submitted to the region, for example. Someone has to sign this design. Who is going to sign this design? The producer of the isolator? No, you will just say, look, I give you the properties after it's your business to do the design. Another thing is that very often they help the designer to do the design. But in the end, who signs, who is responsible is the designer, it's not the producer of the isolator. Of course, the producer of the isolator is responsible to make sure that this isolator, for example, will keep the same properties over time, which was not the case, as you know, for some of the isolators here in L'Aquila. Because they did some tests after some years, after 10 years, they found out that the friction, for example, is no longer the same. For example, is increased. So if the friction increased, it means that this isolator is not going to work for the design earthquake. So perhaps you design this isolator to work for an acceleration, peak acceleration 0.25 g, instead the isolator doesn't work until 0.40 g. Maybe it doesn't work until 0.40 g, means that you have designed everything elastically, instead something may plasticize inside there. So it's a bit of a problem with the isolator. We need to make sure that the properties will be kept constant over time, which didn't seem to be the case for some of the buildings we built here. Okay? So it's always the responsibility of the designer, ultimately. But of course, you need to rely on the properties that the producer of the isolator is going to give you. If they tell you, look, I have a certain amount of friction, this friction will be constant over time, then if it doesn't work, it's not your responsibility. Of course, you will be charged at the beginning, but then there will be a legal person, and he will find that it's not your fault, it's fault, of course, of the producer of the isolator, because the isolator didn't perform well. Okay? So, progetto case, the one that you know very well here in L'Aquila, after the earthquake, we have 73-story building with about 1,850 flats, which is quite a big number, if you think, for 6,000 people, built in about 80 days. Also, this is a good to think about compared to how it's going in Amatrice. They have maybe 1/10 of the buildings. So here in L'Aquila, they're still in the tents and with the piles of rubber there. Here, in this respect, they did well here. So, of these buildings, 25% are made of light frame timber, 25% cross panel, 50% reinforced concrete. Now, the important thing that you may know is that actually, if you look at the building, if you look at the first part of the building, suppose that you look only at this part of the building, so what is underneath this floor, you will find that more or less they're all the same. Is it logical to have more or less the same thing underneath if above you have reinforced concrete or timber? We just said that if you have timber, you have 1/5 of the load. So we should have had, in the timber building, we should have had much slender columns and much smaller isolation. Instead, they're all the same. Why they're all the same? Because when they decided to do this project, they were not clear about what to put above this plant. They were just clear that they wanted to make all the passive base isolation because this was considered as the best system to build in an earthquake-prone area. So they basically designed all this part here, assuming that there wouldn't be a reinforced concrete above. To decide later on. And then they decided that some of the buildings were made of timber, some other made of reinforced concrete. Now, for the timber that are made of timber, it's clear that all this design here is largely over-designed. Because it was designed assuming that there would have been above reinforced concrete, while instead they decided to have only a timber building, which is only 1/5 of the weight, which means that less stress. Okay? The point I wanted to make is basically that using timber you can save lots of money in terms of passive base isolation because you need less reinforced concrete underneath to support the structure, and also you have smaller devices, smaller isolation because the stresses are much smaller. On the other hand, with timber we need to be careful about wind. Now here in L'Aquila, wind is not a big problem, I would say. Maybe other places where, for example, California, just to say, where perhaps the wind could be important, could be significant. If the wind is important, you may have a problem with your isolation system because the isolation system doesn't work, or actually it works too much. It works also when you wouldn't want the system to work, so with wind. So, of course, now this is just a kind of chat that we are doing together. You will study how to design a passive base isolation system next year in the course of earthquake engineering. Just keep in mind that you design for the earthquake, but this is not only the earthquake, there may be also the wind. So take into account also the problem of the wind. As I said, in general here in L'Aquila is not a problem, but some other regions may be, particularly if you are in an earthquake-prone area by the sea, that would be a more important, or maybe a very high altitude. Then maybe the wind may be a problem. Okay? Any question about what we saw so far? Okay. So now, as you can see, we are proceeding towards the end of the course, and of course, since we are in an earthquake-prone region, we cannot avoid, we cannot say anything. What to say? We have to say something about seismic design. Also with timber, Of course, it's a bit of a problem if you want, because it would have been nice, it would have been better, like I used to have this course not in the first year but in the second year. In the second year, then you would have already learned something about dynamic, or structure, or whatever, engineering, and so on. But then we had another problem, because when this course was in the second year, you had to do also design with another course, and then the other course was very demanding in terms of design, so in the end we would end up with you doing just the other course and nothing this course. So we decided to swap, because this was in the first year. So we have this as the only project that we have to do, right? No. Which other project we have to do it? Yeah, this is other project like you will see next year what it means to do a project with Dr. Cinuzzi, Professor Cinuzzi. That will be a very next semester, exactly, next semester. So usually I was in parallel with him, and I remember very well all my attempts were unsuccessful to have a project here, because we were 24 hours per day, the students were busy with the other project. So we decided not to swap. Now finally you can say, okay, you can perhaps commit some of your time to do also this project of timber. Of course, seismic is, as I said before, it's an important issue. Perhaps talking about timber is not the most important one, because timber, as we said at the very beginning, is a lightweight material. So it doesn't suffer the same problem as masonry or as reinforced concrete. But nevertheless, you can understand that if you design a 6 or 7 or 8-story building made of timber, you have to take some, or to make some consideration also about seismic, because it may become also important. So although it's not the most important problem, I would say usually, 90% of the failure in timber structure are due to durability. They are not due to earthquake. When you have an earthquake, it's very seldom that you have a failure in a timber structure. For example, remember there was a cross-lamp buildings, a 3 or 4-story cross-lamp buildings, so not very big, being built in Amatrice during the earthquake. This building still stands there without any problem. Of course, 3 or 4 stories is not a big building. But to say this was built, and I was talking with a producer, which are Legno, an enterprise close to Pescara. They were very concerned when they heard about the earthquake. They were looking for the owner, because they were very concerned that something would have happened, and they couldn't find the owner because just was a problem, just went away. And after they said, no, this building was the building, and everything was fine. So in general, I would say most of the problem you can hear about timber, they are, for example, the famous balconies that fell down. Of course, those are just a problem about your building, not a problem about the earthquake itself. Okay? Or you might have a problem of fire, but also this, particularly if you have a solid timber construction, so timber construction made of cross-lamp, it's very hard to make this panel to ignite. You need to go there, I don't know, you can't go there with a match. It doesn't take fire with a match. You have to go there, I would say in Italian with a lanciafiamme, because otherwise you cannot ignite, because it's too big, it's too massive. So also in this case, fire is not a very big problem. So I would say probably the most important problem of timber, what we really need to care about, is about durability, to make sure that all the details are done well in order to make sure that we have no water trapped inside and so on. So this is really the most important problem. Nevertheless, we need to say something, of course, about seismic. So we will start actually talking about not seismic, but just talking about some basic principles on how to design X-lamp panels for out-of-plane bending and shear. Particularly, we'll just discuss about the simplified method, not about the modified angle method, because this year, since we are talking in English, I realized that I spent a bit of more time than usual, so I want to cut something. I will cut some of those topics, perhaps less important and significant. Then we will move towards discussing some basics of seismic resistance of timber buildings. We will then discuss about the choice of the behavior factor Q for different structural systems. For your case, we already decided to take Q factor equal to 1.5. Okay, to consider your single story building as a non-dissipative structure. right? Given this way. Okay. So this will be a non-dissipant period Q equal to 1.5. We will try to identify which one are the dissipative zones for X-ray and light frame buildings. We will talk about overstrength and overdesign, some concept that you already studied 1 year ago when designing your frame. And we will see that with Libra is quite different. So while from reinforced concrete design, the dissipative system was in the frame was the cross-section of the beam close to the joint. Here, we will learn in timber the dissipative region will actually be the connection itself to the joint. Then we'll talk about capacity-based design and some provisions for ductile behavior of connections. And finally, distribution of lateral forces in the different walls of X-ray and light frame buildings and design by hand. In fact, what I was also last year, what I taught a little bit was how to use finite element models. But this, with up to 1,000, this takes a lot of time, so I prefer not to do this, just to understand how to do it by hand. And perhaps to have you doing a small design of a small building, like a 2 or 3 story light frame or cross-line building, very small, and to do by hand the calculation of the different stories, not by computer, because by computer will take too long. Just to have an idea, flavor of how to do this kind of calculation. So, we start with giving some basics for cross-lamp materials. We already learned what is a cross-lamp panel, what is made, the advantages. And now when it comes to designing a mixed-lamp member, perhaps here we didn't say anything, so it's time now to say something. So, there is a simplified theory. So we can use a simplified theory to design a cross-lamp panel, the simplified theory is based on those two hypotheses, which are, if you look well, they are more or less always the same. So, first hypothesis, only the different blunt layers perpendicular to the design section carry the load. You remember we already been discussing this. If we have a cross section like this, if you have a cross section like this, subjected to, for example, out of plane bending moment or axial force, or even in plane bending moment. So bending moment applied in this direction here. The idea is that which layer will carry this load, so which layer will have sigma carrying these loads here? All 3 layers? No. Which layers will be the one that we have to consider in our verification, for example? So, yes, if you have a cross section like this, subjected to in-plane or out-of-plane bending moment, which layers of those cross section will resist the load? Eh? Which one is that? Only this?
Which direction?
Well, yes, this one. This is the bending moment. So, a panel uses a flow. Out of plane bending moment, what can I expect to have the sigma here? Which layer can I expect to be resistant for this panel?
the fiber along the...
Yes, so this bending moment here will induce sigma in which direction? In the direction, let's call it x, y, or z. So this will be the ny, no? This bending moment ny will induce some sigma, right? So this sigma will be oriented in which direction? In x. So if they're in x, which layer are resistant, which one they are not? The two outer layers. Why the two outer layers? Because they have the fiber, because their fiber is parallel to x. Okay? So in a cross section like this, what about the intermediate one? Is taking any stress, the intermediate one? Something, but very little. Why very little? Because it is oriented in the wrong direction. If you remember, the young modulus is very low also in this direction, so it's very low. So in the end, designing an X-lam cross section like this, I can, in the simplified theory, I can say only the timber plank layers perpendicular to the design section carry the load. So in this case, the resistant cross section will be only this, made only by these two layers, 1 and 2. Okay? So in a simplified theory, I can assume that I have a cross section where the intermediate layer is not there. Of course, this is different if I have an mx moment. In the mx moment, in the other direction, which are the layers resisting? Yeah, in this case we will get some stresses parallel to y. So which layer will be resisting? Exactly. So in the other direction we have this difference. There. Only this is the resisting cross section. Okay? So this is for the bending moment for the out of plane bending moment. Then we have the axial forces. So let's put it here. This will be M Y. This will be M X. The axial forces. So this axial force will be Mx. So for Mx, does something change? For the force Mx, does anything change here? The resisting cross section is the same or is different by the axial force Mx. What do you think? If you have this axial force acting in this direction, what is the resisting cross section? Is the same as before or is something different? Exactly, it's exactly the same. Because again, this just think about this Nx, which kind of sigma is going to induce? Always sigma x. So like before, only this two layer will be resisting. So same thing will be here. And y. Okay? Then we could have also some torsional moment. So we could have some torsional moment like this. It could be M. We could call it YZ. And also here M ZY. Then we could have in-plane shear and out-of-plane shear. Here to direction. Now we're going to spend some words talking about shear, because shear is a slightly different case, a bit more complex to start with. But in terms of bending moment and axial force, I think this should be very clear so far how to do it. One case, only this, the other case, only this. Okay, the second hypothesis, you can see here, the plane section remains plane, namely there is perfect bond among the resisting timber layers. So this is the normal hypothesis that we have done throughout the course of mechanics of material and throughout also the course of reinforced concrete design. So plane section, so section initially plane, remain planes after the formation. This means that we will be able also here to use, strictly speaking, or we won't need it also the method of the transform section. There is actually a more accurate theory, the so-called modified gamma method, where we keep into account also that this hypothesis of plane section remaining plane is not actually 100% true. Why? Because there is an intermediate layer which is flexible. It's very flexible in shear. So strictly speaking, using this modified gamma method, there is a possibility to take into account also the actual shear, additional shear deformation that we have due to the flexibility of the inner layer. But this here we will just ignore this effect. So, out of plane bending, so plane section remains plane, as we said here, you can see, so the distribution of the sigma is linear using the Navier formula. So we can use the Navier formula with the only difference being that we don't consider the whole rectangle, but we just consider the two layers in one side and one layer in the other one. Okay? So if you have, of course, 5 layers, we ignore the 2 intermediate layers that are perpendicular to the grain. If you want, this distribution here comes from the hypothesis that plane section remains plane, so there is perfect bond between the layers, which are glued actually. And second thing, that we are ignoring the resistance and the stiffness of the layer perpendicular to the grain. If you want, assumption, you see E90 equal to 0. E90, so the E of this intermediate layer is equal to 0. It's like if we have no material inside. So calculation of the maximum design bending stress using the Navier formula, sigma equal maximum bending moment divided by KCLT. So KCLT would be the bending or the flexural stiffness of the cross section. So the flexural stiffness of the cross section is basically, if you want, is the second moment of area of this cross section with respect to the neutral axis. Okay? So the second moment of area of this cross section with respect to the neutral axis is the second moment of area of the rectangle with respect to the centroid plus the transportation moment. So plus the area times the distance squared. Do I need to tell you again this kind of thing, or is if you need to calculate the second moment of area of this white area, you know how to do it? I think you should. So you calculate, you see here the formula. Second moment of area of the rectangle with respect to the centroid. So B, in this case, would be, this is T, and this is B. Let's call this one JY, this would be Y. So JY is the second moment of area, one of those white rectangles, so B, T cube divided by 12, okay, plus what, in order to get the second moment of area with respect to Y, plus B times T times for the sake of simplicity, this is T and this is T, so the thickness is the same. Area times what?
T to the power.
Come sorry?
T to the power.
Okay, let's see the distance between the central and the center of the cross section, which is half T plus half T, so T times T to the power of 2. Everything times 2, because we have half above and half below. Okay? And then this one we should multiply to get the K, the flexural stiffness. We should multiply by which value? E 90 or E 0? E mean or E characteristic? So to get the bending stiffness, do I need to multiply by which young modulus? 90 degree or 0 degree first, and the mean value or characteristic value. Actually, the Navier formula is not even needed, because the Navier formula produces sigma max equals bending moment n divided by jy times the maximum distance, which is 3/2 times t. Okay? But of course, if I want to use this general formula, taking into account also the module of elasticity, then of course you can use also the module of elasticity here, and you can cancel it out. Which module of elasticity do I need to use here? Is the module of elasticity parallel to the grain or perpendicular to the grain? Parallel to the grain, because as we said, we know the other one is equal to 0, right? So parallel to the grain, and then the mean value of the characteristic value. Because if you look at the regulation, you find the mean value and the characteristic value. Which value should we use? The mean or the characteristic? You remember when to use the mean and when to use the characteristic?
The mean value.
The mean value. We usually use the mean value. We use the characteristic when? The characteristic used, no, be careful here. The mean is used for serviceability and for ultimate limit state. Why it is not used here? This is ultimate limit state, but why it is not used here?
It is the upper.
Because for ultimate limit state, we are really, the young modulus is going to affect the ultimate limit state only when we talk about buckling, flexural buckling. Here it does not affect. In fact, you can see that if you put the E here, then you can simplify with the E above here. So it's not really needed. Here it's not really needed. So the flexural stiffness is needed when? It's needed when we calculate the deflection. So then we use the mean value. Instead, the characteristic value of the young modulus is needed when it affects the ultimate limit state. So this is the case when we have buckling of either flexural buckling or lateral buckling. In this case, we need to use the characteristic value of the module of elasticity. Okay? So basically for a mixed-up structure, we can use very simply the formula of the two mechanics of structure. So if you have a bending, sigma max, like in this case, sigma max and sigma max with this formula. Okay? If you have an axial force, so this is sigma max n. Sigma max n, what will be the distribution of forces due to an axial force? So how can we calculate now the sigma max due to n? First of all, it's right to write sigma max due to axial force. what is the distribution of the stresses due to an axial force in this cross section? If I apply an axial force tensile or compression force here, what kind of distribution can I get? Okay, so uniform where? Everywhere? No. Only on the resisting rectangle. So we have something like this. Okay? So this means that sigma max n will be n divided by a. We can call this one ay, where ay will be twice b times t. Okay? Clear? Okay? Now, of course, if you have to do the verification of the opposite cross section, there will be some difference related to the fact that here we have only one rectangle as a resisting one, and it is on the neutral axis. So here we will have a distribution of sigma like this, due to bending, and a distribution of sigma like this due to axial force. The formula will be similar. In this case, we will have only BTQ divided by 12 for the bending, and BT for the axial force. Okay? In the other cross section. It's clear? So, in terms of axial forces and bending moment, out of plane bending moment, I think that it should be clear how to do. Okay? Now I think we can finish, for sure, because we are late. And tomorrow we are going to talk instead about the shear, because the shear is a slightly more complex problem here. Because you will see that what we spoke, what we introduced some days or some months ago, rolling shear, we never use rolling shear. When we check the cross component, we will have to use the rolling shear. In this case, we may have the rolling shear as a stress acting in our layer. Okay, thank you very much, and see you tomorrow morning. Quindi nel dentro presto inserire un asse già formato.